here's the plan. The plan is we are going to go into AP Physics. So the school year's about to start. AP Physics is, well, anyway, so there's 4 different versions of AP Physics, apparently. Okay, so there's a mechanics course C, AP Physics C. This is AP Physics C something else. Right here, there's AP Physics 2, there's AP Physics 1, and they all cover different things. I'm not totally sure how this works. I didn't take AP Physics when I was in high school. In fact, I didn't really like my physics class when I was in high school, but I got better. So I did a compendium or a correlation of the different AP Physics classes. So here's AP Physics 1, 2, 3, and 4. And then these are the chapters, or these are the topics that are covered from the different curricula that they have outlined. And so there's some correspondence between the two. So AP1 is like physics for med students. This mechanics is more like the AP or like the college course for the engineers. And so the way this is going to work, we're going to start with the material as it's outlined in the different courses. And rather than going over through like what you learn in the material and how the formulas work, we're going to go and explain like what's actually going on. So instead of saying, you know, here's a ball and it experiences the force of gravity, and then it follows this equation, we're going to get down into the kind of the fundamental aspects of it, to talk about the stuff that I wish I would have learned in high school physics, but I didn't learn in high school physics, and I didn't even learn this stuff until in graduate school. Okay, so we will start with nothing that appears in the first 2 units. Now, I will admit up front, I'm a little bit nervous about doing this because these are going to be single take, very little editing in the end, me shooting from the hip covering this topics. And so there's a lot to go over, and I may, throughout the course of the next few months as we go through this, need to change the way that I do my drawing pad. But I like the drawing pad that I have because it keeps my head pointed up instead of tilting my head forward so that you can see the top of my head. Anyways, we will figure it out. We'll figure it out as we go. There might be some adjustments as the time comes. But the basic idea is we'll go through all the stuff that's in the AP Physics curriculum, and we'll do it the way that it ought to have been taught from the beginning. One other item of business to discuss, or that I wanted to mention, is that I will be using this as my, where's the thumbnails? Here we go. As my reference material. Okay, so this is college physics for AP courses. Let me switch this view back to continuous. Continuous scroll. College physics for AP courses right here. This is a reference material that is from OpenStax. So OpenStax. Let's see, does it say it right here? OpenStax, like that. So OpenStax is a series of textbooks that are available for free online. It's run through Rice University, which is a name brand American Institution of Higher Learning. And so this is what I'll be using, so that way anyone who wants to follow along is welcome to do so. You know, you can download your own copy of it. And there you go. This is an interesting organization chart that shows how the interconnectedness of all of these physics principles, which we will get to when we get to it. All right, so that's the plan. Here we go. AP Physics, the way that it ought to have been taught. This first lecture, or this first portion, is not covered in the physics curriculum, at least in any depth. But it's really interesting, and so we're going to do it. And that is, in order to understand, so physics is just a description of how the universe works. We want to come up with some kind of model, some kind of mathematical model, you know, a set of formulas or something like that, that we can use to predict the behavior of different matter in different environments. Okay, but in order to do this, you have to be able to map. Since you want to have a mathematical model, you need to be able to map the physical universe, or like whatever your system happens to be, into mathematics. You need to be able to take some object existing in space and time, or some system of objects existing in space and time, and convert that, translate it into a mathematical equation that you can then use facts and logic to calculate how that object will behave going forward. Let's see. So after this, I won't be questioning physics when I look at the quantum world. No, there's no questioning physics after this. Everyone will be amazed at this. Okay, so one of the things that we need to cover before we do that, in order to, like, how do you make this mathematical map, is that we need to understand what are the quantities that we will put into the mathematics. So, you have some formula, you're going to put in variables that represent the mass, or that represent time, or that represent distance. First of all, we don't know what mass, time, and distance are. And second, how those things are connected to a mathematical formulation is another question. So this textbook starts off with this section on physical quantities and units. And the system of units that everybody uses everywhere in the world except for a few places like America is the SI unit, the International System of Units, which is the metric system. Now, the truth is that in the United States of America, the British system has been mapped onto the metric system. So the metric system is the fundamental unit system of the world. And then the inch is now defined as in terms of centimeters or in terms of meters, and not the other way around. So even though we might think here in America that we are using inches and feet and pounds and stuff like that, the fact of the matter is those have all been mapped onto the SI unit system. So the SI unit system, when it changes, if you were to change the definition of the meter, then the definition of the inch would change as a consequence. They are now connected. All right, so the SI system of units. Let me pull up. I have a screen somewhere that has the SI units. Now the SI system of units changed in 2019. And I believe this may be the last change that they do, but we'll find out. Okay, there are, what, 8? 1, 2, is this 8? 1, 2, 3, 4, 5, 6. There are seven units in the SI system. So SI, again, is the International System of Units. There are 8 units that, or I just said 7. There are 7 units that exist in this system. One of them is the meter, so that's a unit of length. There is the second, which is a unit of time. There is the kilogram, which is a unit of mass. Now, the system of units that we use, let me pull up the drawing pad, is called the MKS. Here we go, MKS. So that is meters, kilogram, seconds. So physicists and engineers all use or at least in this textbook, they use the MKS system, meters, kilograms, and seconds. This is not the only system of units that you have based upon the metric system. There's another one that astronomers use, which makes no sense to me, and I've never actually liked the fact that astronomers use it, called the CGS system. So the CGS system is centimeters, grams, and seconds instead of meters, kilograms, and seconds. Now, why would they use centimeters, grams, and seconds? I have no idea. Why would you measure the mass of a star in grams and as opposed to kilograms? And so, anyways, this is the system. It's got weird quantities for things like ergs and dynes and stuff like that, as opposed to joules. And anyways, so there you go. Jansky's is a great unit. CGS, we won't be talking about the CGS other than to mention that it exists, but it is also a metric-based system, centimeters, grams, and seconds. The MKS system, which is meters, kilograms, and seconds, that's what the international system uses. Again, there are 8, and I keep saying that wrong, there are not 8, there are 7 fundamental units in this system. And the 3 most important ones are distance, 3 most important ones in my opinion, and as evidenced by this abbreviation, that is the mass, which is the kilogram. You've got length, that says length, by the way, TH, that's an H, and time. Okay, so mass, length, and time. This is kilograms, meters, and seconds. Now, the other things that are on here, the other units that are in this system are the mole, which is a non-unit, the candela, which is also a non-unit, the Kelvin, which is an important unit, that's a measure of temperature, but it's also kind of a non-unit, and the ampere, and that one is a real unit. Now, so what does this mean? What do these different things mean? So the second is a unit of time, the meter is a unit of length, the kilogram is a unit of mass, The ampere is a unit of electric current, so that gives you the electric charge. How do you measure electric charge? The Kelvin is a measure of temperature. Temperature itself is a measure of the speed or the energy, the random motion of particles in a given system or a given environment. So you have a room filled with gas, you have stuff flopping around or whizzing around in that field of gas. You need to quantify that motion. You quantify that motion in terms of kelvins. So this is actually a macroscopic manifestation of the microscopic behavior that is the motion of the particles measured in meters and seconds and kilograms. Nevertheless, we have that unit of Kelvin. The candela is a measure of the luminous intensity. I think it's luminous intensity is what it's called. This is a unit that I've never actually had to use a candela ever in my history of being a physicist. But if I made electric light bulbs, I would have to use the candela. It's basically when you have an object that is emitting light, how much of that light is visible, exists within the visible spectrum is the candela. And so this actually is an interesting unit because it includes the eye's response to the light that's coming off. So it's how bright does something appear. And so this actually is a translation between the physical properties of something. You have some object that's emitting light at a variety of wavelengths. So say you have the sun that emits light in the infrared and the ultraviolet and everywhere in between. And then it maps it into the response for the human eye. So the candela is actually a unit that takes physics and maps it to some extent into biology. So we're going to go with that. We're going to go with that model. The candela maps physics into human perception and biology. Who is bothering me? Scam likely is bothering me. At the same time, you have something like the Kelvin, which maps the physics of something into the thermodynamic properties of that same object. You have the mole. So the mole is a number. It's actually a pure number, kind of like a dozen. A mole is essentially the same thing as a dozen. It's some fixed number of objects. It's a very large fixed number of objects. It's 10 to the 23 objects, which is basically 10 to the 23 is roughly the number of grains of sand that the Earth has on it. So 1 mole of hydrogen, for example, a mole of hydrogen would be 1 gram, something like that. A mole of hydrogen is 1 gram. Yeah. And that would mean that you have 1 hydrogen atom for every grain of sand on the Earth, roughly. So it's a pure number. It's not really a unit. It's a conversion, on the other hand, between the microscopic physics of the system into the chemistry of the system. So when you're doing chemistry, we don't talk about chemistry much. We try to avoid it as much as possible. But when we do have to talk about chemistry, we'll typically do things in terms of, you have so many grams of salt and you put that in here, or milligrams and things like that. And how you translate the chemistry, which is, how do you manipulate macroscopic scoops of different substances that smell or have other sorts of problems. How do you map that onto the physics of the individual particles? You have to go from grams down to particles, and that happens through the mole. So the Kelvin, the candela, and the mole are all units in the international system that take you from the underlying physics into the realm of chemistry, biology, and thermodynamics. Okay, now, the SI system, or this system, has been around for a few hundred years, but it's changed over time. So originally, for example, the meter was defined as 1/10,000,000th of the distance between the North Pole and the equator down. It wouldn't have been the prime meridian. It would have probably been we can pretend it's the prime meridian because it's basically the same. But I suspect that it was originally done from the North Pole down to the equator, running through the Paris Observatory, because back in the day, the British and the French were competing for who is the most important people in the world. The prime meridian, eventually the British won with the prime meridian going through the observatory at Greenwich, England, which is just outside of London, as opposed to running through the Paris Observatory. So when you visit the Paris Observatory, you will see they've bricked in the line that was the French version of the prime meridian. But Paris and London actually don't, or Paris and Greenwich don't actually line up, and so they're slightly different from each other. We in the world have adopted the British prime meridian, but my suspicion is, although I can't confirm this would be something for someone to look up, that the meter was 1/10,000,000th of the distance from the North Pole to the equator running through Paris, but that difference is going to be tiny between the two. So Now that you run into a number of problems, like what happens when you have high tide or when the moon comes over that part of the Earth, and the Earth distorts in shape, and so the length changes. So that wasn't good enough, and so they kept refining these things as they made improved measurements, or as they had higher precision instruments that they were using to measure different things. They had to come up with more stable or better standards with which to measure something. Because the issue you face is when you go to a different country, how does everybody know that they're looking at the same stuff? Like, how this is a 12 ounce can of Space Pop, right? Space Pop right there. You can see through it. So space soda right here. How do we know it's 12 ounces? It says it's 12 ounces on it, but do we actually believe them? And if I were to buy this in a different country, 355 milliliters, so I were to buy this anywhere except for Myanmar, and it's 355 milliliters, how do I know that I'm actually getting 355 French milliliters instead of 355 American milliliters? And the answer to that question is we've agreed on this system, and that system is calibrated across the whole planet. And the way that it used to be done was, for many of these things, you would either set up a hypothetical situation, or you would come up with some definition, or you would have an actual object that was the definition of the system or the thing that you're talking about. So, for example, the big K, the kilogram right here. So this was the kilogram artifact. That's this guy. Let's see, open image, view image, a new tab, I guess we'll go with that. So this is the kilogram artifact. In here is a cylinder of some kind of alloy, and a palladium iridium alloy, or platinum iridium alloy that was roughly square in the side profile and then round at the top. So it's a cylinder, and it weighed 1 kilogram, and it was for a long time the kilogram. So if someone were to sneeze on this kilogram, that would change the mass of the kilogram, which means that all the rest of the kilograms in the whole world were wrong, immediately became wrong. So this was the definition of the kilogram, and there were copies made of this thing that were sent around to all of the different nations so that they could have a standard by which to measure their kilogram. And so what will happen is, in the United States, this is controlled by the Commerce Department at the National Institute for Standards and Technology, which is NIST. So NIST has a few locations. One of them is outside of Washington, D.C., has another location. They have research locations that are run through the Department of Commerce to make better metrology, to make better instruments that we consumers can use to ensure that when we cut 8 feet of lumber, that it's actually 8 feet long. And so what will happen then is each individual country will say, okay, here's the standard, and you can have NIST come out and calibrate your instruments. So if you're making precision medical instruments and you need to have you need to manufacture parts that behave or the right size, you can have your instruments calibrated by NIST or by some other institute that will calibrate their own instruments and then come and calibrate your instruments. That way, these things are standard across the whole globe. So it's not a trivial thing to make sure that everyone knows what they're talking about when it says, how much are we going to weigh? What is the standard that we use for weights and measures around the world? So this was the standard for the kilogram up until 2019. But there are other things that existed. So there was, for example, the meter, which was made out of the same alloy, kept at a specific temperature, and located in the same location in France. It was a 1 meter long piece of this same material. So that way it wouldn't expand or contract very much, and it was impervious to it was easy to purify it so that it didn't have a lot of iron deposits and stuff like that in it. So all of these things, all these units, the kilogram and the meter in particular, had artifacts that they used to determine their length for something like almost 100 years. For the kilogram, it was even longer. The copies of the kilogram had been recalibrated. So they made copies of the kilogram. The real kilogram, the big K, was located in Paris. The other ones were weighed relative to that. And so that way you knew how much to knock off, like what fraction of the mass it was over or under when you fabricate them, because you can't fabricate anything perfectly. Then they were shipped around the world. At one point, they were brought back to Paris, and they were recalibrated. And it had shown that the masses of all of these objects, the copies, had spread out over time. And that could be through the absorption of ambient hydrogen or ambient helium that's in the air, and it gets embedded inside there, and then that's more mass in the kilogram. There's all sorts of ways that the mass of things can change by just interacting with the atmosphere. Even though it's held under vacuum, over the course of a century, things can leak in and then embed themselves in that. So it's pretty gnarly. A few other things, for example, the ampere, which is a measure of electric current, how much electric current is passing through a wire. This was set up by a hypothetical situation that would never arise in real life. Basically, the idea was you have two wires that are infinitesimally thin, which you can't make, and you put them exactly 1 meter aside, 1 meter away from each other, which you can't do because there's no way to place them exactly 1 meter apart from each other. There's always going to be some uncertainty. And then you run electric current through them, and those wires are going to exert a force on each other because that's what electric charges do when they're moving. And when the force between those two wires is equal to 1 Newton, which is a unit of force, then you have 1 amp going through the system, which seems like a really unusual way of measuring the amp, is by setting up a thought experiment with these two wires and then running the experiment and saying, okay, now we've got an amp, as opposed to what an amp actually measures, which is how many electrons pass by in a given second. So this was one of the issues that we were facing when it came to the unit system, is that this is an artifact that can change its mass through interactions with whatever. This is something, a hypothetical situation that you can't ever have. The second, this is an atomic clock. So it used to be that a second was 1/84,600th of a day. But then it turns out that when you have an earthquake, the day changes in length by an amount that you can now measure. So if you have an earthquake somewhere, the Earth changes its shape a little bit. That changes the rotation rate, which changes the length of the day. And so as our instruments got more precise, you can't have the old unit doesn't work anymore, because you need a precision that's better than what you actually get in the real universe that we live in. And so improved clocks. So for a long time it was quartz oscillations, and then it was this cesium transition with an atomic clock. At some point, maybe we'll talk about atomic clocks, but not today. So there's this atomic clock that has a very specific oscillation frequency, and you count the number of oscillations of that atomic clock, and that defines the second. So that's a fairly recent addition. I think that happened I don't remember. It happened back in the day. 1983, it changed from that quartz vibrations up to this atomic clock. But this is the way the system of units worked. There were some things that you could measure, or some things that you could define. So there's this atomic clock that you could measure. There's the speed of light, which was defined. It used to be that the speed of light was defined as how far light traveled in a second. And now the speed of light is specified. This is the speed of light, and the meter is measured relative to the speed of light. So that's a change. The speed of light is the fundamental constant, and the meter is now defined in terms of the speed of light, instead of the other way around, which is what it used to be. This right here says that this was the International Prototype of the Kilogram, MIPK. That's the mass of the International Prototype of the Kilogram. That defined what the kilogram was. This fundamental constant tells you what the amp is. The triple point of water right here, that's an interesting thing. So the triple point of water is, let me pull that up, since at some point we'll get into this. Water phase diagram. So we can get rid of this. So here's the water phase diagram. Oh, that's an ugly one. Is this better? That looks better. All right, this is the water phase diagram. So this is pressure. So atmospheric pressure is right here. This is temperature right here. So you can see that water will freeze at 0 degrees Celsius. It will boil at 100 degrees Celsius at atmospheric pressure. If you raise the atmospheric pressure, or you raise the pressure like this, it will freeze at colder temperatures. So you can get water that's liquid to freeze if you raise the pressure. You can get it to freeze at lower temperatures. You can get it to freeze. Yeah, you can get it to freeze at lower temperatures if you raise the pressure. It's easier to freeze if you raise the pressure. So to the point where you can get liquid water, and if you squish it hard enough, you'll get it to freeze directly at room temperature. So And then if you continue to heat the water, you'll go through this liquid. So this is the liquid phase of the water. And then it will turn into a gas once you pass the boiling point, which is 100 C. If you raise the pressure, it takes more energy, has to be at a higher temperature in order to boil the water. Okay, so these things run downwards. You have solid phases over here, you have the liquid phase in the middle, you have the gaseous phase over here, and you reach the triple point where water can exist as a vapor, a liquid, and a solid at the same time in equilibrium. And so there's only one place, there's only one set of physical conditions in the whole universe where water can do this, and that's the triple point. And so the way they defined the Kelvin, which is a unit of temperature, is they said, okay, this triple point of water is unique. And so whatever the temperature is for the triple point of water, so you come down here, that determines what the Kelvin is. And then you divide it up and you chop it up into degrees, although you chop it up into kelvins. So that's how you define temperature, is by the triple point of water. In this case, they're using atmospheres, but it doesn't matter if it's atmospheres or pascals. So pascals is a SI unit of pressure. The point is that the triple point is fixed. Regardless of the unit system that you're using, that exists, that's a very specific physical condition, however you map that onto a unit system, your unit system of choice. And then it tells you, calculating the Kelvin, the size of the Kelvin, and the location of absolute zero is determined by, you find the triple point and then you divide it up into 273.18 or something like that pieces. And that gets you both the size of the Kelvin and the location of absolute zero. Let's see. So here's a question. They're using atmosphere instead of pascals because it doesn't matter. So as what number is the triple point defined? So the triple point is defined because the universe, like water molecules, choose what the triple point is. The physics of water molecules chooses what the triple point is. And then we simply say, oh, the triple point of water corresponds to so many kelvins. And we can also define it, the pressure, that way if we wanted to, but we don't. So again, this is only, by how many Kelvin is it? The size of the Kelvin. Wait, the size of the Kelvin? No, you get the size of the Kelvin. So the Kelvin is like a degree. 1 Kelvin is the same size as 1 degree Celsius. Let's see. So we'll pull this up here. 1 Kelvin is the same as 1 degree Celsius. But the question is, how many kelvins does it take to go from absolute zero up to the triple point? And that's how you define the Kelvin. So you fix the intercept, you fix the y-intercept at 0, and then you fix the triple point and tell the person how many times you have to divide that up. Into how many pieces you have to divide it in order to get that. Okay, now this is the Ancien Regime. This is how the system was from 1983 until 2019. In 2019, it was a big deal for all 10 people in the world who care about this. And now there's more. But it was a big deal, this switch in the SI system of units in 2019, because historically, some of these were artifacts. Some of them were determined by other things that depended upon these artifacts. Like this mu naught depends upon the mass of this, right? The kilogram tells you what the amp is. The meter tells you what the amp is. The second tells you what the amp is. The kilogram tells you what the mole was, right? Because it was the number of carbon-12 atoms in something. And so all of these things were dictated by kind of external forces or external artifacts. And what they wanted to do is to move all of these things to fundamental constants. So things in the universe that exist that don't change. And like the speed of light, for example. The speed of light does not change. And so the meter being defined in terms of the speed of light means that the meter will no longer change. And it also means that any individual nation can come up with, you don't have to have an artifact that you compare around the world. You set up a standard based upon these fundamental constants, and then anyone can make a meter that works. So the triple point is defined as 273.16 Kelvin. And that's pretty close to 0 C. Yeah, exactly. So it's like, 0.1 away from, 0.01 degrees away from the freezing point. The freezing point at atmospheric pressure. Okay, so we don't need the water phase diagram anymore. All right, so the new system of units looks like this. It's way more symmetrical, and it makes everyone feel warm and fuzzy on the inside. So let's open up this thing. So this is the new system of SI units. We already seen the speed of light, so that didn't change. The oscillation frequency of the cesium atomic clock, that also did not change, and so that gives us the second. H right here, that is Planck's constant. Planck's constant is a fundamental constant that was incorporated or devised to explain things in quantum mechanics about 130 years ago. And Planck's constant is now what is used to give you the kilogram. The Avogadro's number is a fixed number now. So Avogadro's number is now a fixed quantity. Instead of saying whatever the mass of 12 grams of carbon 12 is, you just say this is Avogadro's number, 6 point something something times 10 to the 23. That gives you the mole. Notice that it's completely detached from all the other units, which is an indication that chemistry is not a real science. Candela is the same as it was before. The Boltzmann's constant, so this is Planck's constant up here. I hope I said that right. This is Planck's constant up here. And then this down here is Boltzmann's constant. So that is something that's used to measure when you're talking about the behavior of individual atoms in a system. You typically will use Boltzmann's constant for entropy and gas expanding, and Boltzmann constant, what comes into thermodynamics. That gives you the Kelvin. So Boltzmann constant is a fundamental constant of the universe. And now the Kelvin is defined in terms of Boltzmann's constant. So what you do is you fix Boltzmann's constant, and that tells you what the Kelvin is. You fix Planck's constant, and that tells you what the kilogram is. You fix, in this case, the electric charge. The electric charge is now a fixed quantity. It's constant that cannot change anymore. You don't measure the electric charge anymore. You define the electric charge, and then the amp is purely based upon now the electric charge and the second. Electric charge per second is the amp, where it used to be that the amp was defined in terms of this constant, which depended upon a bunch of stuff, and the meter and the second. Now, the amp is determined by the charge on the electron and the second. So this is a huge improvement in the system. It simplifies it in that these are all fundamental constants that you can define. You can measure what they are, but if you were to make a measurement at the speed of light and you found that it wasn't what you expected, you would change the definition of the meter, not the definition of the speed of light. That's pretty cool. Now, this candela, someone mentioned that they didn't really understand candela. I don't totally understand candela either. I will say what this does is it says you have some object that's glowing brightly, and then you have to say how much of that glowing brightness actually lands in the visible spectrum, and then that's how you determine what a candela is. It's not just how bright is something, it's how bright does something appear to the human eye, which means that you actually have to have a model for how the human eye responds to things, and everybody's eyes are a little bit different. And so they have a theoretical model basically that says this is roughly the human eye response, and then you get the candela from it. So it's a bit weird. So mu naught is, this mu naught that was here is fundamentally related to C, but it's also related to the kilogram. In order to get the amp, all of these things have to go in to give you the amp, and mu naught was this kind of, it was defined in terms of epsilon naught, and so it was a messy situation. You can tell by how asymmetric this system of units looks. So that is, I agree that it seems, so the comment, it seems unscientific for a unit to depend on humans. I agree. But that's what it is, right? This is, how do you translate it to biology is what that basically boils down to. How do you take the candela and transform it into biology? So there you go. That is the system of units. And so we need this system of units in order to be able to take what we observe in the universe and map it onto a mathematical model. Not only do we need a system of units, but we need to have a way of relating those units to the mathematics. So let me go, let's see, SI unit system. So these are the only units that exist in the SI unit system. Everything else is derived from them. So for example, if velocity is the meters per second, that's not a fundamental unit. Okay, big G, Newton's constant, is not a fundamental unit. You construct these other units from these ones. So the force of gravity between two objects, big G, has units of Newton's meters squared per kilogram squared. And so you have to come over here, pick from this table the units that you're working with, and put them together in order to get other things. So that could be meters per second squared. It could be pressure, so pascals in pressure. is constructed by using these units. These are the fundamental ones. Everything else depends upon this system. Are probes, SCVs, and drones fundamental units? They're like fundamental units. In the StarCraft universe, they would be fundamental units, yes. All right. So that is that portion, the system of units. Okay, the next thing that you have to do if you want to, isn't the mole dimensionless? Yes, the mole is dimensionless. It's like a dozen. So this comes up in chemistry all the time. It's like, what does it mean to have a mole of something? It's just a number of objects. It's an actual number. It really doesn't have units. It's like saying a dozen is important. I'm going to elevate the dozen to, in this system of SI units, we should have a dozen right here, and it's 12. Unless you're a baker, in which case it's 13. And so that's something that's weird about Avogadro's number, is that it's just a number. But that's the world we live in, and so we have to keep the chemists happy, and so we'll go with it. All right. Now, how do you map this stuff onto reality? That means that you have to have a coordinate system. And in particular, we'll go back to this meters, kilograms, and seconds, because that's really the basis of all this stuff. The electric charge is its own unique thing that will take some stream at some point in the future. The meters, kilograms, and seconds, how do you map this onto a coordinate system? There's a variety of different ways to construct coordinate systems, and not all of them are, well, they all have their own advantages. So you can have a coordinate system, we typically will say, well, here's your coordinate system, it looks like this, and you've got some x direction and some y direction, y, x like this. But this isn't all that's going on. So let's just say that you have a single coordinate. Okay, let's say you have a single coordinate here that looks like this. So this is the x direction, and this is also in the x direction, except it's going to be some special x. So we'll call it x prime because we don't have anything better to call it. So these are two different coordinate systems. You could imagine having a coordinate system where all of the divisions are equally spaced, like this. Or you could imagine a coordinate system where the divisions are not equally spaced, like that, where they spread out. Why would somebody do such a thing? I don't know. Maybe it has to do with the farther away you live from the city center, the more widely separated the streets are. Maybe it has to do with constant separations in, say, the amount of mass in the atmosphere. So the atmosphere gets thinner as you go up, and so you could say, well, I want to define when I have some fraction of the atmosphere within, I'm going to define a new coordinate system where I have 1% of the atmosphere with each thing. So for example, let's say that I start with the surface of the Earth, and I want to say, I'm going to divide the atmosphere up into chunks up to, we'll say up to 100 kilometers. No, I don't even need to say that. And let's say that I want to have, here is 1% of the atmosphere. Here's the next 1%, so that's 2% of the atmosphere. Here's the next one, 3%, 4, 5, and then these are going to spread out because the atmosphere gets thinner as you go up. So I could imagine having a coordinate system where I'd want, this is how I map each individual percentage of the mass in the atmosphere onto some system, and these coordinates are going to spread out. There's a variety of reasons why you would have a coordinate system that spreads out like this. Okay, so here, for example, is one coordinate system. So this is x, going back to what I had, this is x prime. This one might have equally spaced, at least from our point of view. And this one could have unequally spaced things from our point of view. All right, so what does this mean? Well, let's suppose that you have an object that's moving along here. You would say, it's moving at a constant speed because it passes each of these tick marks at some fixed time interval. So here's a time interval, and it's going to pass its next tick mark in that same time interval all across as it moves across the thing. We say, well, look at that. It's moving, and it's passing all of these tick marks uniformly, and so I will say that that's traveling at a constant velocity. So constant velocity, that says constant. On this hand, if you take that same object and you look at it in this coordinate system, what would you say? You would say, this object starts off in one tick going some distance, but it's a distance that's greater than the tick marks on that coordinate system. And then here, that's one more tick, and then here's one more tick, and it's traveling less and less distance in this coordinate system. So you'd say to yourself, this object's actually slowing down as it moves from one side to the other. At least someone living in this coordinate system, someone living here, watching that object pass along this coordinate system would say, this object is slowing down because it's passing my coordinate system markers less and less frequency according to my clock, let's assume that their clocks are the same. And so the coordinate system means something. Like, it's how the coordinate system is laid out affects how you would map what's happening onto your mathematical model. Because your mathematical model is, I'm going to map distance onto a number line. I'm going to say, here's some distance in space, and I'm going to take that distance and I'm going to map it onto a number line. So here's the number line that I'm going to use. So there's the distance, and I lay it across there, and then I partition my universe up into pieces of whatever the lengths are. So this is actually something that comes up in Einstein's theory of gravity, is that Einstein's theory of gravity says the universe actually, when you have mass in some area or energy in some area, it actually distorts the coordinate system like this. And so when you're falling through space, you're not actually accelerating. What you're doing is you're moving at a constant speed in a coordinate system where the length changes. The length of your coordinates change in that particular direction because it's being distorted by nearby mass, as opposed to here it is and I'm moving at a constant speed in some direction. Now, typically certainly for this class, and for almost all physics classes that one would ever take, you would have a coordinate system where all of these intervals are equidistant from each other. Okay. Now, another thing that can happen is you could have a coordinate system that has multiple directions. So that's a one-dimensional coordinate system. You could imagine having a two-dimensional coordinate system, okay, like this. So this could be y and this could be x, but that doesn't necessarily have to be y or x, right? This could be like up, down, and this could be the side. And this coordinate system could also, have its own, you could have different units on different axes. You could have one measured in one unit and one measured in a completely different unit. You could measure this direction in meters. You could measure this direction in kilometers. So all of these things are up to the user. How am I going to define the coordinate system? So naturally, there's standard systems that people said, okay, let's just pretend for a minute that we all agree on what all these things should be. And people will typically say, well, if you're talking about dimensions in space, then you're going to have, this is going to be the horizontal direction, this is going to be the vertical direction, and we want them to be measured in some standard unit, like meters, and so then you'll partition it up in some uniform way in both directions. But it doesn't have to be vertical and horizontal. You could imagine having a system that's set up like this, where you define your own coordinate system in this way, like down the block and up this way, perpendicular to the block's surface. Or you could have physics where you have the same problem set up, a ball rolling down a hill, whatever the case may be, and you choose to keep the coordinate system like this. So this is going to be horizontal and this is going to be vertical. Vertical relative to what? Well, vertical relative to like the pull of gravity, presumably. Okay. One thing about physics is that regardless of the coordinate system that one chooses, whether you choose the coordinate system that is, I guess, tied to your the scenario that you're looking at, or the coordinate system that's tied to the overall environment around your system, you have to get the same result. And that's something that's interesting about physics, or an important physics principle is this idea of invariance, that this physical situation of, here's the Earth down here, here's an inclined plane, here's a ball rolling down the inclined plane. It doesn't matter what your coordinate system is, that whatever is observed, in order for your theory or for your mathematical model to be consistent, it has to get the same result regardless of the coordinate system that you use to measure it. So if your coordinate system is pointed in some direction, and then you rotate that direction, you remap your language into this new coordinate system, but the physical result of the ball rolling down the hill, that has to be the same. That is invariant. And so that's an important thing in physics, is the idea of that physics happens and the universe doesn't care what coordinate system you're using. The universe is going to do something And then you are going to take your knowledge and what you observe, you're going to put a coordinate system on it and map how what you observe onto the coordinate system and construct the mathematics around that. So this is something to consider. Another thing to consider is the fact that the coordinate system that you use, typically use in a physics class, is one where these two things are independent of each other. That motion in the vertical direction is independent of motion in the horizontal direction. Or if you have a plane, an inclined plane like this, that motion along the plane is independent of motion perpendicular to the plane. This need not always be the case. You can imagine systems, and this happens a lot in different branches of physics, where your coordinate system actually is not perpendicular to each other. The different axes are not perpendicular to each other. So here's an example of that. You can have a coordinate system where there's some angle that's not 90 degrees. So this is not equal to 90 degrees. And so motion in one direction also translates into motion along the other direction. This happens, anytime you have city streets that are laid out that aren't in a grid, you would have this. The place that this shows up the most that I know of is in condensed matter physics, when you're studying the properties of a crystal lattice. So you have a crystal lattice where you have different atoms that are located at different locations like this. So you'll get hexagonal close packing, which corresponds to, if I did this right, so here's hexagonal close packing. You see that it forms this hexagon. So this would be like nanotubes, carbon nanotubes. Carbon atoms will arrange themselves like this. And so then you would say, well, here's one axis that goes in this direction, and here's another axis that goes in this direction, because the unit cell is actually this wedge, or this rhombus-shaped thing right there between all these different components. So this is the way you would construct a unit cell, and notice that they're not perpendicular to each other. And so you can have coordinate systems where the two things aren't perpendicular to each other. In fact, you could do the inclined plane thing where you also have coordinate systems where the things aren't perpendicular to each other. It just changes how you construct your mathematical model to map what you observe onto the mathematical description. So something to be aware of with coordinate systems is that it's really up to us, the user, to choose the coordinate system that we want. And we would want to have, in general, we will choose coordinate systems that are most convenient for what we're doing. So for example, it's a lot more convenient when you have two spatial directions that you need to worry about to have those spatial directions perpendicular to each other, because that means that motion in one direction is completely independent of motion in the other direction. You can push something in one coordinate, if you have an ordered pair, here's an ordered pair that has like an X and a Y coordinate, I'm going to say, okay, this is going to be the X direction, north-south is going to be the Y direction, east-west is going to be the X direction, although that's, again, an arbitrary thing. Or it's not arbitrary, it's a thing that you make by choice. And so I can move this one, I can change this value here without changing that value and that corresponds to moving in one coordinate direction and not moving in the other coordinate direction. So there's all sorts of ways that one would construct a coordinate system. And in general, the important things are, when you're making a coordinate system, are going to be things that people will look for in your coordinate system is that they are perpendicular. That says perpendicular. Also, a way to say this is orthogonal. Okay. Number two, that if you're talking about the same unit, if you're measuring the same unit, so if it's meters in this direction and meters in this direction, that you want them to be the same. So you want, let me say that again. If you want this to be a distance in this direction, and you want it to be a distance in this direction, typically you will have them be the same. So you'll have them what are called normalized. So that this distance will be measured in meters, and this distance up here will also be measured in meters. If this is east-west and that's north-south, and you want everything measured in meters, you'll typically do that. That doesn't always happen. So I can think of an example in astronomy where you have, in one direction, you'll have something like kilometers, and in the other direction, you'll have like megaparsecs, okay, which are not the same unit at all. This is a huge number of kilometers to get a megaparsec. So there are specific situations in a given discipline where you could imagine having a coordinate system that has the same dimensions, like dimension of distance in both directions, but in one side it's measured in one unit, and in another side it's measured in a different unit. But for the most part, certainly in this course, they will be normalized so that it's always the same unit. It'll be meters in one direction or meters in another direction. But that's just something to keep in mind, that these rules are in place more for convenience than they are because that must be the way that things are. The only thing that a physical model has to do is it has to describe what's happening in the universe. And how you choose to label that, how you choose to translate it into mathematics, that's up to you. You can make your life easy by choosing an orthogonal axes, perpendicular axes that are independent of each other and normalize so that the units are the same, or you can choose something that's a bit harder by having British systems and metric system on different axes. So that is that's pretty cool. That amount of choice, typically, you don't think about how much choice do I have in my coordinate system. And the answer is you have a lot. All right, let's see. Did I do anything? So the SI unit system, you transform between meters, seconds, kilograms, and coulombs and stuff like that. That's something for your one's teacher to go through. Talked about this, the speed of light. We'll go into the speed of light a little bit different. There's these prefixes that go into there. You have to convert between them. And that's, accuracy, precision, and significant figures. So this is actually something that's also interesting. Generally speaking, when the way that science operates, the way that physics operates, is a bit different than maybe the way that it's, well, I'll tell you how it operates and then you can decide if it's different than what you thought. Okay, let's suppose that we want to measure some quantity. Let's suppose that we want to, measure big G. We want to measure the strength of gravity. Okay, so we have, over time, we'll measure the strength of gravity. So this is time, and this goes back to, when was big G first measured? Big G was first measured with the Cavendish experiment. That was like in, 1789 or 1780 something, or 1796 or something like that, in the 1700s. So in the 1700s, the first measurement of big G was made, and it turned out to be some value, 6 point something, 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 something. Okay, times 10 to the minus 11. And then as time goes on, those measurements improved, and our uncertainty in those measurements changed. So the first time big G was measured, that was by Henry Cavendish, and it had some uncertainty associated with it. So he's like, here is the measurement I made, and I know that I've got it, that it's probably a little bit wrong. I can estimate how far away from the real value I am based upon the quality of my measurement. As time goes on, you can make better instruments because you make a lathe which makes more consistent instruments. You can calibrate that based on this, and then with each iteration, with each new set of instruments, you can make improvements in the measurement. And so over time, the measurement uncertainty will get smaller. So how well you can place something, or how precisely you can measure something, gets smaller. Okay, and then it will get smaller still from there. Okay, now in the case of big G, there's no way to predict what it is. So maybe big G was a bad example for what to do. What would be a better example? Oh, I got a better example. So there's a thing, a value for a quantity related to the electron that is equal to 2.001 blah, 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 blah. It's a really long thing, and you can calculate. We have a theory that predicts what this value should be. So we have an interplay between theory and experiment. So we have a way to predict from using fundamental constants and mathematical models what this quantity should be. It's called the lambda G factor. Okay, and it's almost 2, but not quite 2. So we have a theory that predicts what these decimal places should be. And so we turn things over to the theorist and we say, okay, calculate what this should be. And the theorists come along and say, okay, well, we know it's 2 point something, 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 and we start filling in these decimal places here. And then what you do is you go back to the experiment and you say, all right, does the theory actually work? So you have an experiment where you trap an electron in an atom and you look at how it spins and you hit it with a laser beam and then you put a magnetic field on it and then you stare at it without blinking for a while and then you change the altitude or whatever. You do all sorts of things to this experiment and you measure this quantity. So here's your experimental measurement and you keep going, and at some point there's a disagreement. There'll be a disagreement between the theory and the experiment, at which point you do one of two things. Either you look at your experiment and you say, are we doing something wrong? Or you look at your theory and you say, did we miss something in our calculation? And until you can rectify that disagreement. Once you've identified, maybe it turns out that they forgot some calculation in the theory. And so they went back and said, oh, we missed this thing. I'm going to go back and I'm going to include that now in the theory and start adding more digits of precision. And then you do another set of experiments and you come along, and then there's another disagreement now later on at some other decimal point. So this one disagrees, now they disagree in the 10th decimal point. And then you say, is this a theory problem or is it an experimental problem? And then maybe the experiment this time, it turns out that there's something that we were using to calibrate our experiment, and that calibration was wrong. That it turns out that the kilogram mass was slightly different from the calibration mass that we were using, and so when we go and we calibrate it to the mass of the big K in Paris, then we can change what our experimental apparatus, we can adjust our experiment, and then we start doing it again. And then you start making measurements and making predictions and matching them up. And as this continues, it does two things. One is it requires that you improve the precision of your measurements, and also the precision of your theory, but generally speaking, the precision of the theory comes from limitations due to computational power. So you typically don't talk about precision when it comes to theory, but it can come in based upon computational aspect, like highly technical details. When it comes to experiment, the precision is basically how well can I reproduce my result? What are the things that are affecting my result? So the precision is the size of your uncertainty in your measurement. So you make a measurement, you have some uncertainty in what that measurement is, this is the precision. And you can shrink that precision down by, one way you can shrink the precision down is by making repeated measurements using the same instrument. You make repeated measurements, there's some fluctuation because a butterfly flapped its wings, and that caused this to jump up a little bit, and then you did it again, and this time the butterfly unflapped its wings, and so it causes it to vary a little bit the other direction. And so repeated measurements with the same instrument is going to give you some idea of the precision of your measurement. You can improve it by having more and more and more measurements, and that will shrink down what the value is at the center. Eventually, you run into another issue that you have to confront, and that is the accuracy. These two things are not the same. Accuracy and precision are very much different from each other. The accuracy is related to bias, and the precision is related to reproducibility, reproduction. Okay, so reproduction meaning, can you reproduce your measurement? If you do one measurement and then you do it again, then you do it again, do you keep getting the same result? So if you can reproduce your result, that means you have high precision, and the precision is within what tolerance can we reproduce the result. The accuracy is the bias. So an example of an experiment that was inaccurate is there was a group that I was working with, I didn't work with them, but that was at my institution in graduate school. And it turns out that the screws that they built their apparatus out of had been calibrated using the wrong length. So the definition of the inch changed in the 1983. The inch used to be its own unit, and then it was moved onto the metric system. When it was moved onto the metric system, the conversion between centimeters and inches changed, and some bolt manufacturers didn't change with the times. And so you had this experimental apparatus that was built by these physicists, and they were doing the actual conversion of from inches, because it was a bolt that they were using that had some number of threads per inch. They were converting from inches to meters, so they knew how many turns of the screw corresponded to how many meters. However, because this instrument the bolts were not calibrated properly, they didn't follow the metric system they didn't follow the system of units a decade and a half after it was done, after the change was made. It meant that the results were always the wrong. When they made these turns of the screw, it produced the wrong distance. So they thought that it corresponded to 1 centimeter of change, but instead it corresponded to 0.997 centimeters of change. And as a consequence, that biased their results. So their results were inaccurate. They kept making measurements, but the measurements were always offset and always in the same direction because of some bias to their apparatus. So that is how the way to improve the accuracy of something is to remove bias. So one way to remove the bias in in an experiment is to calibrate your experiment really well so that all of your parts actually behave the way that you think they are. You can have bias because maybe you're working with a metal alloy that has contaminants in it, and that changes the magnetic properties of it. So there's a lot of reasons why bias could creep into an experiment. The way that bias can creep into a theory is, for example, that you might be missing something in the theory that turns out to be important. So here's an example of a theory that is biased: gravity. Newton's law of gravity turns out isn't actually correct. That there's some changes that you need to make in Newton's law of gravity. So Einstein's theory of gravity, if we assume that Einstein's theory of gravity is exactly correct everywhere, which, well, so far there's no evidence to the contrary, but we suspect that it will have to break down at some point because we need to connect it with quantum mechanics. But Newton's theory of gravity, we know, breaks down, and so it's accurate up to some number of decimal places at the surface of the Earth, but it's not accurate to infinity decimal places at the surface of the Earth. So if we're looking at the surface of the Earth, and let's say we want to measure something to nine digits. So we have a, or like 3 point something, 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 and then 9 digits later we have an 8, calculated by Newton's theory. So this is Newton. It turns out that Einstein would say, no, this is actually 3 point something, 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 and I get a 5 here at the end. This indicates that Newton's theory is actually inaccurate. Okay, it's not that it's imprecise. It gives you, a theory generally gives you exactly some number, but it's inaccurate. It's missing some physics. It's missing some aspect of the physical world or the universe that we live in that needs to be accounted for in order to correct it from what Newton's theory predicts and to what Einstein's theory tells us that it should be. Of course, and like I mentioned, this is also assuming that Einstein's theory is exactly correct, which is the current assumption, especially when it comes to these kinds of things. Einstein's theory is going to be correct up to, maybe another 10 decimal places or something like that before it turns out to be inaccurate, or an inaccurate measure of the quantities that we care about. So we know that gravity between Newton and Einstein disagree at the 9th decimal place because the timing precision that you have in the GPS system needs to have general relativity corrections incorporated into it. The GPS satellite system that goes around us is accurate to nanoseconds, so that's 9 decimal places. And if it didn't use Einstein's theory, it wouldn't be accurate to that level. So anyway, something to keep in mind. That indicates that Newton's theory is inaccurate. It's incredibly precise because it gives you exactly the same number. You put numbers in, you get some numbers out, and you will always exactly reproduce those calculations. However, it's inaccurate. It gives you wrong answers. So the question becomes, is the inaccuracy of Newton's theory of gravity too big of a deal? Is the inaccuracy something that we need to worry about, or is it something that we don't need to worry about? And so here's what you would do. You would say, okay, here is my scenario. And I have Newton's theory of gravity. I'm doing calculations with Newton's theory of gravity. And I need to make a measurement. I'm going to make a measurement that is precise to, some uncertainty like this. So Newton's theory of gravity makes a prediction. Here is the prediction from Newton's theory of gravity. And here is my measurement, and my measurement looks like that. Not a big deal. So I missed the prediction. So this is the prediction, and this is the measurement. My measurement has some uncertainty. It's got some precision. And I didn't get exactly what was said there, but I got it to within my uncertainty. Okay, so no problem. If you were to come back and do another experiment, so you improve your apparatus to improve the precision of your apparatus, and then you make the same measurement, and it turns out that you get something that looks like this. Okay, so now your new measurement is up here. You still miss, but now your precision is way smaller. So now you have a problem. The measurement disagrees with what the prediction is. And so now you have to go back to both parties and say, okay, what's going on here? Why are we wrong? Or why do we disagree with each other? The experimentalist can go back through his apparatus and say, oh, I can fix all this, I can do this thing, and I keep making the measurement and I keep reproducing it. I'm pretty confident that the issue is not on my side, that my instrument is not biased, that I'm getting, I keep getting the same result. And I've gone back, I've thought of everything I possibly could, and as I make corrections, I keep getting the same result. Then you can go back to the theory and say, okay, why is the theory wrong? And in this instance, for example, you could say, oh, we have to account for the fact that the Earth's gravitational field distorts space-time, and so when you do the prediction with Einstein's theory of gravity, you get this number, like that. So there's going to be this interplay between, as the precision of your instruments improves, that forces you to have improvements in the accuracy of both the instrument and the theory that you're using to make the measurement. For most of the things that happen in this, in the first year of physics class, these are subtleties that don't really come up. But if you're doing cutting edge research in some area, then this is the name of the game, is how do we improve the accuracy and precision of our measurements, and then how do we compare that to a theory, and then which one needs to change. So a good example of where this recently came out was the experiment at Fermilab. This was just a few months ago. Fermilab announced a result from their muon G-2 experiment, which is similar to that electron experiment that I mentioned, where you count the decimal places and then the theory predicts some number of decimal places. And now there's a disagreement between what the theory predicts and what the experiment measures. And so now both groups of people need to go back and say, all right, what are we doing? How can we improve the accuracy and the accuracy of the theory and the accuracy and the precision of the experiment? In that case, they also have to improve the precision of the theory, because there are a number of different groups that are using different algorithms to calculate what the value should be, and those algorithms actually have some disagreement between each other. So that's where you can get a precision measurement on a theory, is if you have, in that case, you're running into how do you compute something using the finite capabilities of a terrestrial computer. So anyways, there we go. So accuracy, precision, coordinate systems, and unit systems, those are all aspects of physics that kind of get glossed over in the first few lessons, but that are important. Okay, does anybody have any questions? Let's see, I guess if Einstein never came up with a theory, we could have been thinking our experiments were always wrong. Yeah, exactly. So if Einstein didn't come up with a theory, as our measurements of astronomical events improved, the precession of Mercury was always an issue. Like, Mercury's orbit was advancing, it was changing its orientation, and we didn't have a good explanation for it. We, the scientists, tried a number of things, or we, humanity, tried a number of things to explain why Mercury was changing its orbit, and it wasn't working. And so Einstein came along, said, here's a way that you can change the orbit, and in addition to that, I predict other behavior. And then it took several tries, but eventually they saw the fact that the gravitational field of the sun also distorted the apparent positions of stars in the sky that were, kind of close to the limb of the sun. It took a total eclipse, and it took World War I, I guess, got in the way. But eventually they confirmed that Einstein's prediction about the positions of stars in the sky relative to the sun did indeed change according to the way that his theory predicted. So Newton's theory is not accurate because it misses this, basically. Newton's theory assumes that in a gravitational field, all of these divisions are equidistant, that these are all meters. Einstein says, no, that's not actually how it works, that in a gravitational field, so this is Earth down here, in a gravitational field, these things actually they get bigger, or they change their shape or their size as you get closer to the Earth. And so Newton's theory says this is how the coordinate system works. Einstein's theory says this is how the coordinate system works. And as a consequence, Newton became less and less accurate because these things didn't correspond to each other. Those distances didn't correspond to each other. So there you go. Let's see. Internal validity within the context of individual study. This type of bias is also called internal validity. So I agree that was only a 1 sigma disagreement, but anyways, that's what it was. If both are wrong, wouldn't you end up in an endless cycle, never getting it right? So if both the theory and the experiment are right, then, as long as both of you are making improvements, then eventually you should get some agreement. Can I think of a situation where, right now there's disagreement between theory and experiment, and it could be that both of them are right, or both of them are wrong. I don't know, okay, it can't be that both of them are right. So that definitely can't be. There's disagreement between what we observe and what our mathematical mapping of the universe tells us we should be observing. Those disagree. So either the experiment is wrong, And the result that was interesting is the fact that the experimental result that just came out matched a previous experimental result that also disagreed with the theory. So now we have 2 experimental measurements that disagree with the theory. And so that is a stronger indication that it's the theory that's wrong and not the experiment that's wrong. And so then people say, oh, that's new physics. We've discovered something new, because our experiments are continue to reproduce some value that is different from what the theory predicts it should be. And so we need to go back and find out what's missing from the theory. Okay, let's see. Which one caused those superluminal neutrino measurements that were rejected later? So another example of an experiment that got a result that disagreed was this neutrinos that were moving faster than the speed of light. This was in, what, 2011? Thank you for that sub, King's Throne. I appreciate that. 45 months. 45 months. That's almost 4 years. In fact, so that means that it's been 4 years since I started streaming. 4 years and a couple months. Wow, that's a long time. All right, let's see. So the superluminal neutrino measurements, so neutrinos moving faster than the speed of light, was rejected. That happened to be a cable that wasn't connected properly, and so they were getting some spurious signal. Let's see, return to the same point after traveling 2 pi r distance. Can there be loops? Oh, that's a great question. So can there be loops in the coordinates? Yes, you can have a coordinate system. I mean, you might have a physical system where you're looking at something like a cylinder. So you can have a physical system where you can move in this direction and you can move in that direction, where as you move, so this is a coordinate system where it slides around like this and you come back to where you started from. You can also have a coordinate system where, rather than measuring in this direction, and they both have the same unit, you measure a radial distance and an angle. So instead of having x and y, instead you have an r and this angle theta. So that is something that can happen. You can have a similar coordinate system that still defines, still spans 2-dimensional space. So here's an interesting thing, is this coordinate system, you have meters in this direction, you have meters in this direction. This coordinate system, you have meters in this direction and not meters in that direction. That's weird. Okay, so if you just have a rectangular Cartesian coordinate system, you might have meters in the vertical direction and meters in the horizontal direction. But when you do it in the polar coordinate system, where you have an angle and a distance, then you got meters in one direction and no unit in this direction, right? Angles don't have units. Angles are just quantities, because they're always measured in radians, and radians have no units. So a couple things. One is that you can have a point, and you can have an infinity number of coordinate pairs that correspond to that same point, because you can go around this circle as many times as you want and still land there. So that's one interesting phenomenon that arises when you have a coordinate system like this. Another thing that should arise is, how do you get this is 2 spatial dimensions. So if we're mapping a point in 2 spatial dimensions, and you can have one coordinate system that has units of length and units of length, in, like, you have the 2 perpendicular directions and they both have units of length, where did the other unit of length go? You have this unit of length here, and you have this not unit of length there. So it seems like you should be losing information when you go from length and length to length and angle. It turns out where you get the other length from is the arc length right here. So if we were to look at the way that if you have a XY, of course I just had that, let me put it over here. If you have an XY, you have meters here, or like length here, and you have length here, when you move in this direction, you're increasing a length. And when you move in this direction, you're also increasing a length. So it has to do with when you move in a particular direction, what is the length associated with it for a 2-dimensional surface, or in this case, a 2-dimensional space. So with the r and theta thing, the way that it works is, here is r. You can increase in one spatial dimension. If you increase r, you're increasing a length, right? So this is your radius. And if you move in that direction, you're increasing a length. In the tangential direction, so in the theta direction here, it is this length, the length that is perpendicular to the radius that you're changing. Okay, and that's going to be, so in this case, a little bit of length will be dx for those who love calculus, which is everybody. And in this case, it will be dy that corresponds to that direction. And that's just assuming that X and Y are the ones the directions you care about. In this case, it will be dr that moves in that direction, and in this direction, that is going to be r times d theta. So that's the arc length that you have right here. And theta has to be measured in radians because that is the unit of angle, not degrees. Degrees are for losers and sissies. Theta is measured in radians at a fundamental level. So this length that you increase when you increase the theta direction, it's r d theta that you're changing. And it's dr if you're moving in the radial direction. So there are these different kinds of coordinate systems. You can have coordinate systems that are even more weird than this. You can have like these hyperbolic coordinate systems where you have like weird kind of ellipses that come around, and then this kind of spreads out in weird directions. There's a variety of ways of mapping two-dimensional surfaces onto each other. You can also run into issues where you have distortions in the surface that like if you have a sphere, you're mapping something onto a surface of a sphere. So, but hopefully we come across some more of those examples at a later time. All right, let's see if I'm missing anything else. Newton's theory is not accurate because it doesn't account for the distortion of spacetime. I think I mentioned that. I wonder if there was ever a theory that was wrong, but it somehow matched experiments. Has there ever been a theory that is wrong, but somehow matched experiments? Yes. So the theory about the Earth at the center of the universe was wrong, but matched observations up to some level of accuracy, or up to some level of precision. So you could do, well, another example would be even Kepler's laws. So Kepler's laws of planetary motion are wrong, but they agreed with experiments up to the ability to make those measurements at the time. As measurements have improved, then we've refined Kepler's laws to incorporate Newton's theory of gravity and eventually Einstein's theory of gravity. So those are examples of something that was wrong, but matched experiments up until the point that the experiments got precise enough to be able to point out the discrepancy. It really takes, the reason that you continue to do physics experiments is because the physics experiments, you increase the precision, and hopefully you have accuracy, you have a pre-existing accuracy, and you increase the precision of those measurements, so that, or the accuracy and the precision, you improve on those two coordinates, those two quantities, the accuracy and the precision of your measurement, up till the point where you find the disagreement, and then that helps you refine your theory. That's generally the orbit, or the thing that it works. Let's see. Diagram made me think of a question I had. If any three-dimensional coordinate system can be mapped onto a unique point in a 1D line, why do we then need 3 dimensions? Oh, that's a great question, Puzzle Gamer. Okay, so here's what's going on with this one. There are things called space-filling curves. So a space-filling curve is a single curve that you can map to any point in space to within some uncertainty. So let's say you have a two-dimensional space like this, and I want to identify this point. One way to do it is to say, oh, I can move in this direction, in this x direction, I can move in this y direction this far, and I move in the y direction that far, and I get an ordered pair x, y. And because it's a two-dimensional surface, I need 2 coordinates, one for each dimension to do that. Even if I had a coordinate system where it wasn't perpendicular, I still would need the 2 different measurements in order to arrive at the location, what it would look like this, I guess, to arrive at that location. I still need 2 coordinates to do it because I'm talking about a 2-dimensional surface. I could imagine talking about a 3-dimensional volume, but we're just going to go with 2-dimensional surface and say, okay, I have this map and I need 2 spatial dimensions. If I do r and theta, I need r and r d theta, basically, in order to get to that location. However, there are these quantities these objects called space-filling curves. So a space-filling curve would be, okay, here is my coordinate system. I can start like this. What you have to do is you have to say, all right, I'm going to define a tolerance. I want to be able to pinpoint some location to within this tolerance. You have some uncertainty. Okay, so here's the point that I want to locate. You can start with, you have to iterate. You have to say, okay, here's this. And the question is, does that fit? Does that get within this tolerance of that location? Because if it did, if my tolerance was really big, I could say, oh, that maps to this location on the line. And then I can say, oh, where is that location in space? It corresponds to this location on the line. All right, then I could say, if my tolerance was small, then this doesn't work. And instead I have to iterate on this curve, and I end up with something that I think, let's see if I can draw this properly. It looks like this. Am I doing this right? It looks something like that. Okay, and then I can say, is this point closer or farther from that point? Let me pull up an actual graphic of what it looks like. So it's a space filling curve. Space filling curve. And there's a variety of different ways to do it. This is one example of here's an example of different types of space filling curves that you can have. So this is like one that's built on hexagons. This is one that's built on rectangles. This is one that's built on, well, this is like built on squares. This is built on rectangles. So you have these space filling curves. Let me pull up this one just so that it's easier to see. I can zoom in on it. And so you can say, okay, I want to locate this particular point to within some precision. This curve won't do it. This curve also won't do it. This curve also doesn't do it. But by the time I get to this iteration, you know, I follow it's a single line. Then here's the point that I had in mind. And this line gets to within the tolerance of that point that I had in mind. Therefore, I can map, as long as I have specified a tolerance, so you have to specify the tolerance first, I can go to whatever iteration I need in the space filling curve in order to identify any single point in the plane, like in an arbitrary sized plane, to within that tolerance. So, you know, whatever the tolerance happens to be, you can basically say, as soon as I define the tolerance, whatever one gives you this space here that's smaller than the tolerance, that's the last iteration. Then you can pick any point in space and map it onto a single line. You map it onto a single line. What you miss with that space filling curve, however, is that now, did I draw that shape right? I did draw the shape right. Okay. Now when you have a curve like this, in a two-dimensional system, if you have a point here and a point here that are next to each other, the coordinates are actually going to be next to each other as well. So this could be, let's say that you have 2 points. Here's your thing. There's a point here and a point here. And you say these points are close together in 2 dimensions. And the way you can tell that they're close together in 2 dimensions is because if you take point 1, x1, y1, and you subtract point 2, or let's say you do point 2. Normally you would do 2 minus 1. So point 2 minus point 1, x1, comma y1. You subtract these two things and you're going to get 2 small numbers. Okay, so you have basically delta x and delta y. That's an x. And this is a delta. So these things are much, much less than 1, 1. So it's a small quantity, that uncertainty. On the other hand, when you plot this with a space filling curve, you know, that's wiggling around like that, this point might be up at one part of the curve, and this could be on a completely different part of the curve. So that when you subtract the positions of 2 neighboring points, so now you have 2 neighboring points like this, but the line that goes through them, where's my thing? Here we go. The line that goes through them might go like this, like that. And now, even though they are close together in one way of measuring it, so here they would be considered close together, but on the line, now they're disconnected from each other. So you have, the issue that you confront is that you no longer have spatial correlation in your coordinate system when you have a space filling curve. And it doesn't matter if it's a plane or if it's a 3-dimensional volume that you're mapping on, is that when you map the plane onto a line using one of these curves, the 2 different locations that are spatially connected to each other or spatially near each other in the 2-dimensional coordinate system are no longer near each other in the 1-dimensional coordinate system. So there you go. Kevin Bacon at 6 degrees of separation, he gets a special pass. Let's see. If there's a tolerance, it's not really, no, because the way that so with these space filling curves, like how does it really map onto a plane? Everything in math is, in terms of continuity and stuff like that, and like what does a smooth surface mean? It's all defined by tolerances. So calculus, when you do calculus, especially when you do it in college, it's all epsilon delta. It's like, if I say that within some tolerance what does a continuous function mean? A continuous function means that when you specify a tolerance in the vertical direction, that you can specify a similar tolerance in the horizontal direction, such that the curve doesn't leave the volume that you just specified, that area that you specified. So that's how all of mathematics is constructed, is through tolerances. And so you can do the same thing here. Let's see. All right. I think that wraps it up for today.